In part 1, I showed you how we build the real numbers from 10 axioms. We found that the reals form a complete ordered field, and that completeness is what separates R from the rationals. We have the field. Now we need to get precise. We need to see how decimals approximate any real number. We'll work through the triangle inequality, one of the most used tools in analysis. And then we'll move into a new dimension, the complex numbers. When you write a number like 7.25, what does that actually mean? It means 7 plus 2/10 plus 5/100. More formally, A0 plus A1 over 10 plus A2 over 10 squared, and so on, up to an over 10 to the n. Each digit ai is an integer from 0 to 9. The whole number part, a0, can be any non-negative integer. We call this a finite decimal representation. Every finite decimal is a rational number. If you have a decimal with n digits after the point, you can multiply by 10 to the n to clear the decimal. What you get is an integer divided by a power of 10. 7.25 equals 725 over 100. So finite decimals live inside Q. They form a subset of the rationals. But not every rational number can be written as a finite decimal. Consider 1/3. Suppose, for the sake of contradiction, that 1/3 equals some integer a divided by 10 to the n. Then 3 times a equals 10 to the n. But the prime factors of 10 to the n are only 2's and 5's. 10 to the n equals 2 to the n times 5 to the n. There's no factor of 3 anywhere, so 3 cannot divide 10 to the n. Contradiction. 1/3 has no finite decimal representation. It requires infinitely many digits, 0.333 forever. This is where completeness enters the picture, and I think it's one of the most satisfying applications of the completeness axiom. The completeness axiom guarantees that we can approximate any real number, rational or irrational, to any desired accuracy using finite decimals. Think about the square root of 2. It's irrational, but we can trap it. 1.4 is less than root 2. 1.41 is closer. 1.414 is closer still. Each finite decimal gets us nearer to the target, and we can get as close as we want. Let me make this precise. Take any real number x greater than or equal to 0, and any positive integer n. There exists a finite decimal Rn with exactly n digits after the decimal point, such that Rn is less than or equal to x, and x is less than Rn plus 1 over 10 to the n. We can trap x in an interval of width 1 over 10 to the n. As n increases, this interval shrinks. For n equals 1, the interval has width 1/10. For n equals 2, width 1/100th. For n equals 6, width 1/1,000,000th. Arbitrarily small, arbitrarily precise. How do we actually find these approximating decimals? The proof builds them digit by digit, and I find this construction worth walking through carefully. Start with the set S of all non-negative integers less than or equal to x. 0 is in S, so S is non-empty, and S is bounded above by x. By completeness, S has a supremum. Call it A0. This A0 is the greatest integer in x. We write it as floor of x, or bracket x. If x equals 7.25, then A0 equals 7. Now we find the first digit after the decimal point. Multiply x by 10 and subtract 10 times a0. This isolates the fractional part, scaled up. For x equals 7.25, 10x equals 72.5. Subtract 70. We get 2.5. Take the floor. a1 equals 2. That's the first decimal digit. We continue this process. Multiply, subtract, take the floor. Each step extracts one more digit. The result is a sequence of finite decimals R1, R2, R3, and so on, each one closer to x than the last. And x is the supremum of this sequence. The decimals converge to x from below. The digits a0, a1, a2, a3, and so on, obtained by this process, define an infinite decimal representation of x. We write x equals a0.a1, a2, a3, continuing forever. For rational numbers, this expansion eventually repeats or terminates. For irrational numbers like pi or root 2, it never repeats. The digits go on forever without a pattern. There's a subtlety worth noting, and it confused me the first time I was reading it. A real number can have two different decimal representations. Let's take 1/8, for example, which equals 0.125. We could write it as 0.125000 with zeros forever. But we could also write it as 0.124999 with nines forever. Both represent the same number. Both sequences of finite decimals have the same supremum. Two different names for one number. This shows that two different sets can have the same supremum. Now let's turn to a concept that will appear constantly in analysis: absolute value. For any real number x, the absolute value of x, written with vertical bars, is defined as x if x is greater than or equal to 0, and negative x if x is less than 0. So the absolute value of 3 is 3. The absolute value of negative 3 is also 3. Geometrically, absolute value is distance from 0. If a is non-negative, then the absolute value of x is less than or equal to a if and only if x lies between negative a and positive a. Writing the absolute value of x is less than or equal to a is the same as writing negative a is less than or equal to x is less than or equal to a. Absolute value bounds translate to symmetric intervals around 0. I use this equivalence constantly in proofs, and you will too. Now for one of the most important inequalities in all of mathematics. For any real numbers x and y, the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. The absolute value of the quantity x plus y is less than or equal to the absolute value of x plus the absolute value of y. This is called the triangle inequality. The name comes from geometry. In any triangle, one side is always less than or equal to the sum of the other two sides. You can't take a shortcut through empty space. The direct path from A to B is never longer than going from A to C to B. Algebraically, if you walk x units, then y more units, you end up at most the absolute value of x plus the absolute value of y units from where you started. Possibly less if x and y partially cancel. The triangle inequality takes several useful forms, and I want you to know all of them. Substituting x equals a minus c and y equals c minus b, we get the absolute value of the quantity a minus b is less than or equal to the absolute value of the quantity a minus c, plus the absolute value of the quantity c minus b. This says the distance from A to B is at most the distance from A to C plus the distance from C to B. There's also a reverse triangle inequality. The absolute value of the quantity A plus B is greater than or equal to the absolute value of the quantity, the absolute value of A minus the absolute value of B. The absolute value of a sum is at least the difference of the absolute values. These inequalities are fundamental tools. Memorize them. Another inequality that appears everywhere in analysis, linear algebra, probability, and physics is Cauchy-Schwarz. I consider it one of the most useful inequalities you'll ever learn. If A sub 1 through A sub n and B sub 1 through B sub n are any real numbers, then the square of the sum of A sub k B sub k is less than or equal to the sum of A sub k squared times the sum of B sub k squared. In symbols, the quantity the sum of A sub k B sub k squared is less than or equal to the quantity the sum of A sub k squared times the quantity the sum of B sub k squared. In vector language, this becomes the dot product squared is at most the product of the squared lengths. The quantity A dot B squared is less than or equal to the norm of A squared times the norm of B squared. Taking square roots, the absolute value of A dot B is less than or equal to the norm of A times the norm of B. Geometrically, the dot product equals the norm of A times the norm of B times cosine theta. Since cosine is at most 1 in absolute value, the inequality follows. Equality holds exactly when the vectors are parallel, pointing in the same or opposite directions. The proof is, in my opinion, clean, and I think it's worth seeing. Consider the sum of the quantity A sub kx plus B sub k squared for any real x. This is a sum of squares, so it's non-negative. Expanding, ax squared plus 2bx plus c is greater than or equal to 0, where a is the sum of a sub k squared, b is the sum of a sub k b sub k, and c is the sum of b sub k squared. For this quadratic to be non-negative for all x, its discriminant must be non-positive. 4b squared minus 4ac is at most 0. b squared is at most a times c. That's Cauchy-Schwarz. The entire proof fits at the back of an envelope. Sometimes it's convenient to say that an unbounded set has a supremum. It just happens to be infinite. To make this precise, we adjoin two ideal points to the real numbers, positive infinity and negative infinity. The extended real number system, written R star, consists of all real numbers together with plus infinity and minus infinity. We define arithmetic with infinity as you'd expect. Any finite number plus infinity is infinity. Any finite number minus infinity is negative infinity. Any finite number divided by infinity is 0. If x is positive, then x times infinity is infinity. If x is negative, then x times infinity is negative infinity. And infinity plus infinity is infinity. Some operations are left undefined. Infinity minus infinity, undefined. 0 times infinity, undefined. Infinity divided by infinity, undefined. These are indeterminate forms. They require limits to resolve, as you'll see in calculus. Why bother with R star? Because now every non-empty subset of R has a supremum in R star. If the set is bounded above, the sup is a real number. If it's unbounded above, the sup is positive infinity. No more exceptions. In R star, the supremum always exists. We also define neighborhoods of infinity. The set of all x greater than some large number is a neighborhood of plus infinity. Now we face a fundamental limitation of the real numbers, and I want you to really feel this limitation before we resolve it. The square of any real number is non-negative. Positive times positive is positive. Negative times negative is also positive. So the equation x squared equals -1 has no solution in R. The parabola y equals x squared sits entirely on or above the x-axis. It never touches the line y equals -1. Mathematicians respond to limitations by extending the system, and that's exactly what we'll do. A complex number is an ordered pair of real numbers, written x1, x2. The first component, x1, is called the real part. The second component, x2, is called the imaginary part. Two complex numbers are equal if and only if both their real parts and their imaginary parts are equal. The set of all complex numbers is denoted C. We define addition component-wise. x1, x2 plus y1, y2 equals x1 plus y1, x2 plus y2. Real parts add, imaginary parts add. Multiplication is more interesting. x1, x2 times y1, y2 equals x1, y1 minus x2, y2, x1, y2 plus x2, y1. This formula looks strange at first, but it's designed for a specific purpose, which will become clear shortly. With these definitions, the complex numbers satisfy the commutative, associative, and distributive laws. 0, 0 is the additive identity. 1, 0 is the multiplicative identity. Every non-zero complex number has a multiplicative inverse. C is a field. It has all the algebraic structure of R. Just as real numbers are points on a line, complex numbers are points in a plane. The complex number x1, x2 corresponds to the point with coordinates x1 and x2. The horizontal axis represents the real part. The vertical axis represents the imaginary part. This is called the complex plane, or the Argand diagram, after Jean-Robert Argand, who published this idea in 1806. Gauss had the same idea independently in 1799. In this geometric view, adding complex numbers is the same as vector addition. To add x1, x2, and y1, y2, complete the parallelogram. The sum is the opposite corner. Real parts add horizontally, imaginary parts add vertically. Notice that the real numbers sit inside the complex numbers. The real number x corresponds to the complex number x0, a point on the horizontal axis. Adding and multiplying x0 with y0 gives exactly what you'd expect from real arithmetic. So R is a subset of C. The real line is the horizontal axis of the complex plane. There's one complex number that deserves its own name. The complex number 0, 1 is called I, the imaginary unit. It sits 1 unit above the origin on the positive imaginary axis. With I, we can write any complex number in a familiar form. x1, x2 equals x1 times 1, 0 plus x2 times 0, 1. That's x1 times 1 plus x2 times I, which we write simply as x1 plus I x2. So 3, 2 becomes 3 plus 2I, much cleaner. Now let's compute I squared. This is the moment I hope everything comes together for you. I times I equals the ordered pair 0, 1 times the ordered pair 0, 1. Using our multiplication formula, 0 times 0 minus 1 times 1, 0 times 1 plus 1 times 0 equals the ordered pair -1, 0, which equals -1. I squared equals -1. We've created a number whose square is negative. The equation x squared equals -1 now has a solution. X equals I. There's a geometric interpretation that I find is worthy of being shown for building intuition. Multiplying by I is the same as rotating by 90 degrees counterclockwise. Start with the number 1, sitting on the positive real axis. Multiply by I. You get I sitting on the positive imaginary axis. That's a 90-degree rotation. Multiply by I again. You get I squared, which is -1, another 90 degrees. Two 90-degree rotations make 180 degrees, and one rotated 180 degrees is -1. That's why I squared equals -1. It's geometry. For a complex number z equals x1, x2, we define the modulus or absolute value of z as the absolute value of z equals the square root of x1 squared plus x2 squared. This is the distance from z to the origin. It's the Pythagorean theorem. The complex number x1, x2 is the hypotenuse of a right triangle with legs x1 and x2. The modulus has useful properties. The absolute value of z, w, equals the absolute value of z times the absolute value of w. Multiplying complex numbers multiplies their moduli. The absolute value of z over w equals the absolute value of z divided by the absolute value of w. And for real numbers, this definition agrees with the usual absolute value. The quantity the absolute value of z minus w is the distance between z and w in the complex plane. This makes C a metric space, a set with a notion of distance. And distances satisfy the triangle inequality. For any complex numbers x and y, the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. The same inequality we had for real numbers extends to the complex plane. The direct path from 0 to x plus y is at most as long as going from 0 to x, then from x to x plus y. Can we define less than for complex numbers the way we do for reals? We want an ordering that satisfies the axioms. Trichotomy, addition preserves order. Multiplication by positives preserves order. The answer is no, it's impossible. And the proof is short enough that I want to show you why. Suppose we could order C. Then, since I is not 0, trichotomy says either I is greater than 0 or I is less than 0. Case 1. Assume I is greater than 0. Multiplying positives, I times I should be positive. But I squared equals -1, which is negative. Contradiction. Case 2. Assume I is less than 0. Then negative I is greater than 0. Squaring. Negative I squared should be positive. But negative I squared equals I squared equals -1. Still negative. Contradiction. Both cases fail. C cannot be ordered consistently with the field axioms. This is a fundamental difference between R and C. In real analysis, the exponential function e to the x is central. We want to extend it to complex numbers, preserving the key property. E to the z1 times e to the z2 equals e to the z1 plus z2. For a complex number, z equals x plus iy, we define e to the z equals e to the x plus iy. equals e to the x times cosine y plus I sine y. The real part x controls the magnitude. E to the x stretches or shrinks. The imaginary part y controls the angle. Cosine y plus I sine y determines direction. The heart of this definition is Euler's formula. E to the iy equals cosine y plus I sine y. As y varies, e to the iy traces out the unit circle in the complex plane. When y equals 0, e to the I times 0 equals 1. When y equals pi over 2, e to the I pi over 2 equals I. When y equals pi, e to the I pi equals -1. When y equals 3 pi over 2, e to the I times 3 pi over 2 equals -I. When y equals 2 pi, we're back to 1. The complex exponential is rotation. Set y equal to pi. E to the I pi equals cosine pi plus I sine pi equals -1 plus 0I equals -1. Rearranging, e to the I pi plus 1 equals 0. This is Euler's identity. It connects 5 of the most fundamental constants in mathematics. E, the base of natural logarithms. I, the imaginary unit. Pi, the ratio of circumference to diameter. 1, the multiplicative identity. 0, the additive identity. All united in one equation. I still find it remarkable every time I see it. With this definition, the law of exponents still holds. E to the z1 times e to the z2 equals e to the z1 plus z2. The proof uses the addition formulas for sine and cosine. Complex exponentials behave like real exponentials, but with the added structure of rotation. The complex exponential is never 0, because e to the z times e to the -z equals e to the 0 equals 1. If e to the z were 0, this product would be 0, but it's 1, so e to the z can't be 0. Geometrically, the absolute value of e to the z equals the absolute value of e to the x times the absolute value of e to the iy, equals e to the x times 1 equals e to the x, which is always positive. For real x, the absolute value of e to the ix equals 1. The complex exponential e to the ix always lies on the unit circle. The absolute value of e to the ix squared equals cosine squared x plus sine squared x equals 1. No matter what real number you put in the exponent, e to the ix has modulus 1. When does e to the z equal 1? E to the z equals 1 if and only if z is an integer multiple of 2 pi I. Going around the unit circle, every full rotation of 2 pi brings you back to 1. The complex exponential is periodic, with period 2 pi I. Every non-zero complex number can be written in polar form. Z equals re to the I theta, where r equals the absolute value of z is the modulus, and theta is the angle from the positive real axis. This angle theta is called an argument of z. Arguments are not unique. If theta is an argument, so is theta plus 2 pi, and theta plus 4 pi, and so on. We single out one value, the principal argument, written arg of z, is the unique angle in the interval from negative pi to pi, including pi. For z equals 1, arg of z equals 0. For z equals I, arg of z equals pi over 2. For z equals negative 1, arg of z equals pi. For z equals negative I, arg of z equals negative pi over 2. The payoff of polar coordinates comes with multiplication. To multiply two complex numbers, z1, z2, equals r1 e to the I theta 1 times r2 e to the I theta 2, equals r1, r2 e to the I times theta 1 plus theta 2. Moduli multiply, arguments add. To multiply complex numbers, you scale by one modulus and rotate by one argument. This is the geometric essence of complex multiplication, and once you see it this way, you won't forget it. Raising to the nth power is simple in polar form. Z to the n equals r to the n e to the I n theta. The modulus is raised to the nth power. The argument is multiplied by n. Squaring doubles the angle, cubing triples it. For any integer n, cosine theta plus I sine theta, all raised to the nth power, equals cosine of n theta plus I sine of n theta. This is DeMoivre's theorem. It follows directly from Euler's formula and the law of exponents. Now for roots. If z is non-zero and n is a positive integer, how many nth roots does z have? Exactly n. If z equals r e to the I theta, the nth roots are r to the 1 over n times e to the I times theta plus 2 pi k over n, for k equals 0, 1, 2, up to n minus 1. The nth roots of 1 are particularly elegant, and I want you to visualize them. They're the n complex numbers e to the 2 pi I k over n, for k equals 0 to n minus 1. These are equally spaced points on the unit circle, forming a regular n-gon. The cube roots of 1 form an equilateral triangle. The fourth roots form a square. The fifth roots form a regular pentagon. Algebra meets geometry. The exponential sends z to e to the z. The inverse operation is the logarithm. If e to the w equals z, we call w a logarithm of z. For z equals r e to the I theta, we have w equals natural log of r plus I theta, where natural log of r is the natural log of the modulus. Check. E to the natural log of r plus I theta equals e to the natural log of r times e to the I theta, equals r times e to the I theta equals z. But theta isn't unique. We can use theta plus 2 pi n for any integer n. So z has infinitely many logarithms, differing by multiples of 2 pi I. We define the principal logarithm. Log z equals natural log of the absolute value of z plus I times arg of z, using the principal argument. Log of 1 is 0. That's familiar. Log of negative 1. The absolute value of negative 1 equals 1, so natural log of the absolute value of negative 1 equals 0, and argument of negative 1 equals pi. Logarithm of negative 1 equals I pi. The logarithm of a negative real number is purely imaginary. This connects to Euler's identity. E to the I pi equals negative 1, so log of negative 1 equals I pi. If z is non-zero and w is any complex number, we define z to the w equals e to the w times log z. This generalizes powers to complex exponents. Let me show you something that surprised me when I first saw it. Let's compute I to the I. Log of I equals natural log of the absolute value of I plus I times arg of I equals natural log of 1 plus I times pi over 2 equals I pi over 2. So I to the I equals e to the I times I pi over 2 equals e to the I squared times pi over 2 equals e to the negative pi over 2. I to the I is a real number, approximately 0.208. An imaginary number raised to an imaginary power gives a real result. Complex analysis contains many such results. From Euler's formula, we can derive cosine z equals e to the iz plus e to the negative iz, all divided by 2. Sine z equals e to the iz minus e to the negative iz, all divided by 2i. These formulas define sine and cosine for complex arguments. For real inputs, sine and cosine oscillate between -1 and 1. For complex inputs, they can take any value. If z equals iy is purely imaginary, cosine of iy equals e to the negative y plus e to the y, all divided by 2, which equals hyperbolic cosine of y. This grows without bound as y increases. Complex trigonometry is richer than real trigonometry. We extend C by adding a single point called infinity. The extended complex plane is C star equals C union infinity. 1 infinity, not 2. In R, we need plus infinity and minus infinity because the reals are ordered. There's a positive direction and a negative direction. But C cannot be ordered. There's no consistent notion of positive and negative directions. So there's one way to go to infinity in the complex plane, by letting the modulus grow without bound. All directions lead to the same ideal point. There's an elegant way to visualize C star, and I think it's one of the most beautiful images in mathematics. Place a sphere on top of the complex plane with the south pole touching the origin. Now project. Draw a line from the North Pole through any point on the sphere. Where it hits the plane is the corresponding complex number. Every point on the sphere except the North Pole maps to a complex number. The North Pole itself maps to infinity. This is called stereographic projection. The extended complex plane C star corresponds to the entire sphere, the Riemann sphere. Points far from the origin in the plane correspond to points near the North Pole on the sphere. As you go to infinity in the plane, you approach the North Pole. 1 sphere, 1 infinity. Finite decimals approximate any real number to arbitrary precision, a consequence of completeness. The triangle inequality and Cauchy-Schwarz are fundamental tools of analysis. We extended the reals to include plus and minus infinity, and then we built the complex numbers, a field where every polynomial has roots, where multiplication is rotation, where exponentials and circles collide, where Euler's formula connects exponentials to circles. E to the I pi plus 1 equals 0. 5 constants, 1 equation. This completes the foundation. In Chapter 2, we'll use these tools to study the structure of point sets, open sets, closed sets, compactness, and connectedness. I'll see you there.